Okay, we had another test. Woo! So now let's go through it and let's talk about what we were hoping you would do and maybe a couple of options. And, because it's nice to look and say, oh, that's how you do that. After all, we still have one more test. So it's good to make sure we understand what we need to work on. All right, so cover page, nothing surprising. No, nothing that will shock us. We get our table of Laplace transforms. Other than that, fairly standard. And, let's put our name on it. And today our name will be Solutions. Yes, great name. A very strong, bold name. Okay, so let's start. Number 1. Find a general solution to the non-homogeneous equation y double prime plus 8y prime plus 12y equals cosine 2x. Now, looking at this, we see a couple of things. Obviously, we see the word non-homogeneous, which says, oh, this is a non-homogeneous problem. But we know it's non-homogeneous because there's something right there. Now, when we see something non-homogeneous, we have some options. And in particular, we have 2 options available to us. That is, we have method of undetermined coefficients and variation of parameters. And between the 2, we always have a bias towards the one that's usually easier to run, and that's almost always going to be the method of undetermined coefficients. And so that's what we'll do here. So how do we proceed? Well, we need to start, and the way we'll start is we start with the homogeneous version of the problem. We say, all right, well, let's look at y double prime plus 8y prime plus 12y equals 0. All right, well, that's not that surprising. And what do we do? Well, okay, this turns into a polynomial, r squared plus 8r plus 12 equals 0. And, if we've lived a good life and our teachers like us, and I think they do, they seem like nice people, this will factor. And it does factor. So you need 2 things that multiply to 12 and add to 8. R plus 2, r plus 6. So we say, aha, the roots are negative 2 and negative 6. Now, what this means is that these are going to become parts of our complementary solution, or the solution to the homogeneous part. So we have some constant a, e to the minus 2x, plus some constant b, e to the minus 6x. And we're using x as our variable because we see cosine 2x there. So x is our variable in this problem. All right, so that's the first step we do. In fact, if we were doing variation of parameters, we would still do this first step because we really need to know, hey, what's going on with our homogeneous solution, right? All right, well, now we go to our next step and say, okay, what is the right form, right? If we're doing undetermined coefficients, we need the form. So what we do is we look at the non-homogeneous part and say, okay, cosine 2x, and we say, all right, now what we do is there's a couple rules. If there's powers of x, make sure you have all the lower powers, make sure, take care of any bumping, and sines and cosines come in pairs. So the only rule that we need to worry about, because, see, our function is cosine 2x, that there's no overlap here. There's a pair, sine of 2x. Again, there's no overlap. So that says, aha, our particular solution is going to have the form some constant c, cosine 2x, plus some constant d, sine of 2x, where c and d are to be determined. So most of the rest of this problem is going to be, hey, what should c and d be in order for this to actually work? And what do we mean by work? So that when we plug it in to this differential equation, it holds. Once we have c and d, that means we have our particular solution. And remember, what are we looking for? It should always be, clearly stated at the start of the problem, because it is. What is the goal? And the goal is to find general solution, which means we need to have both the homogeneous part and the particular solution. So it's not find a solution, it's find general solution. So what's next? Well, the goal is we're going to plug this form into that differential equation. so we need to look at the derivatives. So we say, okay, yp prime, that would be minus 2c sine 2x plus 2d cosine 2x. Don't forget the factors of 2 that come from the chain rule. Second derivative, yp double prime, would be minus 4c cosine 2x plus 4d, whoops, not plus, minus, because derivative of cosine is negative sign, sine 2x. You know, it's all right to make small mistakes. Just catch it. You know, always be like, wait, is that right? Is that right? You know, it's okay to ask yourself, hey, whoops, did I make a mistake? And if you did, fix it. Don't just be like, well, you know, it's only one question on one exam. How much could it? No, don't do that. Find your errors and fix them. And the sooner that you find your errors, the better. All right. Well, now we're going to go and plug it in. So remember, we have that cosine of 2x is equal to yp double prime plus 8yp prime plus 12yp. So I'm just copying this down and plugging in the particular solution. So this is yp double prime minus 4c cosine 2x minus 4d sine 2x, all right, plus 8 yp prime, so plus 8, and I'm going to swap the order just so I can have cosines and sines going together. So 2 times d cosine 2x minus 2 times c sine of 2x, and then plus 12, the particular solution, and that would be c cosine 2x plus d sine of 2x, and we're going to tally all that up. What do we get? Well, in front of the cosine 2x, we have minus 4c plus 12c, which makes that grand total of 8c plus 16d, because 8 times 2, and that's cosine 2x. And then in front of the sine 2x, we have minus 4d plus 12d, which is 8d, great. Then we have minus 16c, and that'll be sine of 2x. All right, great. Now, the key here is to say, well, look at the coefficients. See over here, you have a 1 in front of the cosine 2x, so that says 8c plus 16d needs to be 1. You say, well, there's no sine 2x. Exactly. So 8d minus 16c better be 0. Great. So where are we back to? 2 equations and 2 unknowns. What? Isn't that what we're always doing in this class? Yeah, it kind of feels that way, right? Yeah, it kind of does. It kind of does. Okay, so let's move over. We have a little bit of space here. So we will write it down. 8c plus 16d equals 1. And I'll just change the order here. So minus 16c and plus 8d equals 0. Now there's lots of things that we can do. And basically, we can do all sorts of things. You know, set up an augmented matrix, do some substitution. Here, there's easy ways to combine, and so that we get cancellation. If I see easy ways to combine to get cancellation, that's a pretty safe thing for me to do because I don't have to think too hard. And our goal, I don't want to make it sound like, don't think. No, definitely think, but don't think too hard. In other words, don't give yourself opportunities to make mistakes. Try to limit the number of opportunities that mistakes can happen. And so by keeping things simple, that's a good chance that things won't be too bad. Now here, I can see that it's not too hard to cancel the c's. If, for instance, we take the first equation times it by 2, and we take the second equation just as is, so think of it as multiplied by 1. So 16c minus 16c, 0. 32d plus 8d makes 40d. And then, of course, 2 plus 0 is 2. Great. Well, that's wonderful. Now we can solve. This says, hey, d needs to be 2 over 40, 1 over 20. Well, great. Is there anything else we could do? Now, we could, of course, do other computations, but we can do some combining again. And let me move this up a little bit here. So I'm going to use a different color just so we can keep track of, which combining is going where. Okay, so here we go. So on this side, I'll indicate, suppose I wanted to cancel the d's. Well, I'll take this one as is, and I'll multiply this one by -2. And if we did that, what would happen? Well, we'd get 8c plus 32c. That would make 40c. 16d minus 16d would be 0, and that would equal 1, which says that c should be 1 over 40. So now we have our c and d. And so we're ready to give our final answer. So our final answer, here we go, is our general form. We'll start with our homogeneous solution, which is up here, still on the screen. Good. A e to the minus 2x plus b e to the minus 6x, and then add to that our particular solution with the right coefficients. So plus 1 over 20 cosine 2x and plus 1 over 40 sine. Oh, wait, whoops. Did I mix these up? See, d should be 1 over 20. C should be 1 over 40. So yeah, this should be 1 over 40, ha ha ha, and 1 over 20. Yes, transcription errors. Some of the most common errors. And, you never grow out of those. I wish you could say, don't worry, by the time you're nice, you hit your mid-20s, you'll be done with them. No. Okay, so 1/40th, that's what goes in front of the cosine. 1/20th, that's what goes in front of the sine. And there we go. Done. That's it. That's the answer. Okay, so not so bad. Now, could you have done variation of parameters? Yes. Am I going to show you? No, because I don't think it's a very efficient method. You would have had to do some very interesting integrals. That would not be fun to do. And so this was definitely the better choice. And so, make good choices, right? As our parents would want to say to us, make good choices. So that's one problem down. Let's go to our next problem. So, number 2, apply the eigenvalue method to find the general solution of the system. X1 prime equals 5x1 minus 2x2. X2 prime equals 4x1 minus 4x2. And then find the particular solutions, x1 of t and x2 of t, such that x1 of 0 is equal to 5, x2 of 0 equals 6. All right. Now, in some sense, the nice thing here is it tells us what we have to do. There's no choice. It's not like, oh, are we going to do, maybe some sort of elimination method, or are we going to do some eigenvalue method, or are we going to do something else altogether? And no, we're not going to do any of that. We're going to do the eigenvalue method. And the reason we're going to do it is because it tells us. It says do it. So we're going to do it. We're going to follow the instructions because that's the way that we maximize our points, right? We're not going to give them any opportunity to have them take points away from us. No, these are our points, and we're going to fight hard to keep them. So what does it mean, the eigenvalue method? Well, it means eigenvalues, right? So we need to get into matrices. So the first thing we need to do is translate this problem into the language of matrices. So the way that we do that is we say, look, we're going to write this, we're going to let the vector x, we're going to call this x1, x2. And then what we have here, well, we can say x prime, the derivatives, is equal to a matrix times x. And what that matrix is, that matrix will be the matrix of coefficients. So we just copy the coefficients down. 5 minus 2, 4 minus 4. And there we go. All right. So now we say, what comes next? Well, the next thing is for us to find our eigenvalues, our eigenvectors. So we're going to look at the determinant of A minus lambda I. And this determinant will help us find the eigenvalues. So this would be the determinant. So I'm going to take this matrix, this is my A, and I'm going to subtract lambda I, which means subtract lambda on the diagonals. So that would be 5 minus lambda minus 2, 4, and minus 4 minus lambda. Now you can also do, by the way, lambda I minus A. That's perfectly fine. A minus lambda I is a little bit simpler because in some sense, if you're always A minus lambda I, you can consistently work with that matrix. Because there's some places where you do need A minus lambda I. There's some places where it doesn't matter. And so we're in one of the places where it doesn't matter right now. But I think it's good to say, hey, if some places matters, let's always just be consistent. So, you know. Well, anyways, back to our regularly scheduled problem. Okay. What happens here? So we get that this is 5 minus lambda minus 4 minus lambda, subtract 4 times negative 2. Okay, so that's minus 20. Actually, let's do the lambdas first, right? Lambda squared. Then we're going to get a minus 5 lambda plus 4 lambda, which makes it minus lambda, then minus 20, and here be plus 8, right? Because minus 8, plus 8. So minus 20 plus 8 makes minus 12. Now, the moment of truth. Does this factor? And yeah, it will. Because can we think of two numbers that multiply to give negative 12, but add to give negative 1? Yeah. Negative 4, positive 3. So lambda minus 4, lambda plus 3. So we should always check, right? Lambda squared, yeah, that's no surprise. 3 lambda minus 4 lambda, minus lambda, good job. And minus 12. All right, so, and remember, we're setting our determinant equal to 0. And now we're able to say, hey, we can talk about our eigenvalues. Namely, 4 and negative 3. All right, success. We found the eigenvalues. And you might be thinking, hey, it's called the eigenvalue method. So we're basically done, right? Well, it's called the eigenvalue method, but it's really eigenvalue / eigenvector method. And they thought, boy, that's a long name. And so they left out the eigenvector when they were describing the method. So we've got more work to do. We've got to find our eigenvectors. Okay, so here we go. It's going to be a good time. So let's work through it. So suppose we want to do 4. So we're going to look at A minus 4I, because I'm putting in lambda equals 4. Now, I can just come up here and just read off. What happens when I put in lambda equals 4? Well, we get 1 minus 2, and we'll get 4 and minus 8. Now, when we're looking for an eigenvector, then what that says is we're really looking for some vector, AB, such that we multiply it out, we get 0, 0. Now, when it's 2 by 2, it's actually really, really easy. Because you can think of it as a couple different ways. You can say, hey, this means A minus 2B equals 0, and 4A minus 8B equals 0. And you're like, hey, that's the same equation. What? So what we really need is A minus 2B equals 0, or you could say, hey, I just need A to be 2 times B. So our eigenvector looks like this. AB is really 2B, B, and then you can just pull out the factor of B. Because remember, eigenvectors aren't unique. You can always scale. So the claim is 2, 1 is the eigenvector. And so we write it down. Now suppose you were in an exam. Like, I want to make sure I get my points. What could you do to check? Well, what you could do is you could multiply this vector by that matrix. And if you did that, okay, look, 5 times 2 is 10, minus 2 times 1 is minus 2. 10 minus 2 is 8. Well, that's 4 times 2. Next row, 2 times 4 is 8, minus 4. 8 minus 4 is 4. Well, 4 times 1 is 4. So in other words, if you multiply this vector by that matrix, you get 4 times the vector you started with, which means we did it right. Wow. Good job, us. Pat on the back. Okay, well, that was one eigenvalue, but we need 2. And I will comment here, we're in the really nice setting where we have distinct real eigenvalues. If things were complex, we'd have to do a little bit of work. If we had repeated eigenvalues and we were coming up short in the eigenvector department, things would get really interesting. But when we have distinct eigenvectors, like, hey, well, when you have distinct eigenvalues, we're always going to be able to succeed in finding eigenvectors. So it's just like, wow, look at us. We're in the good case. Yes, we are. We are definitely in the good case. All right, I'm going to move this up a little bit. So we're going to go do -3 next. So here we go. So we're going to do a minus 3 times I. So this becomes a plus 3i. Okay, so what is that? Well, so again, it's like we're putting lambda equals -3 there. And so if we do that, we're going to get 2 minus 2. Then we're going to get 4 and minus 1. And I seem to have made a mistake here. I see my mistake. See, I subtracted 3. What was I supposed to subtract? I was supposed to subtract -3. 5 minus -3 is 5 plus 3, which is 8. They might say, wait, how did he catch that mistake? Because it's important to know how to catch mistakes. Well, what was happening was I got to this point, I said, wait a second, these rows don't look like multiples of one another. And if we're in an eigenvalue setting, they have to be. They have to be. Because there has to be redundancy. And so because of that, it's like, oh, I have a mistake. Let's fix the mistake. See how this works? It's like catching the mistakes, making sure we get our points. That's right. That's our goal. That's our goal. Okay, so we're going to multiply this, AB, and we want to get 0, 0. All right, so again, we look at our equations, and because these are multiples of one another, these two rows, there's redundancy. So we get 8a minus 2b should be 0, or 4a minus b equals 0. So that says, hey, 4a minus b should equal 0, or b should equal 4a. So our eigenvalue should look like the following. AB, which should look like a 4a. Pull out the a, 1, 4. And so we get 1, 4 is our other eigenvector. All right, great. So we're doing wonderful. We were able to successfully do our eigenvalues and our eigenvectors. And here's the information. Now, in some sense, we haven't done anything with differential equations. What we've really done is said, starting with this particular matrix, what are the eigenvalues and eigenvectors? In other words, everything up to this point has been linear algebra. But it's been good linear algebra because now the thing becomes, it says, hey, we can use this information to write down the general form. Okay, and we do want that, right? Because it says, find the general solution. So that's part of our answer. So let's talk about our general solution. It would look like some constant, I'll choose a as our constant, e to the eigenvalue, t, times our eigenvector, plus some other constant, e to the eigenvalue, t, times eigenvector. So there is our general form to the system. Okay, now what are we after? Well, remember, then, there's another part. Find the particular solutions and solutions to x1 and x2 such that x1 of 0 equals 5 and x2 of 0 equals 6. So this part right here we could rephrase as saying, look, we want x of 0 to be 5, 6. All right, so that's what we're after. Okay, so we're going to have, well, plug in t equals 0. And the only place it shows up is inside the exponential functions. E to the 0 is 1. So we want a times 2, 1 plus b times 1, 4 to be 5, 6. All right, well, that becomes 2 equations, 2 unknowns. Hey, we've done that. So 2a plus b equals 5, and a plus 4b equals 6. And, well, we look for ways to combine. And ways to combine, hopefully that we can get cancellation. We can cancel the a's pretty easily, right? Just multiply by -2. And if we did that, what would happen? 2a minus 2a, 0. b minus 8b, well, that's -7b. And then 5 minus 12 is -7. So that says, oh, b is actually pretty nice. It's 1. Now, once I know b equals 1, I could come in here because I see, hey, look at this equation. There's just a single b, and I can put it in. Actually, the second equation might be even better. A plus 4b equals 6. So, hey, now that says a plus 4 equals 6. So that says a equals 2. So now we know b and we know a. And so we can make our conclusion that our particular solution is the following. And, well, dramatic pause while we write out particular solution. It's going to be a equals 2. So we'll have 2e to the 4t times 2, 1. And b equals 1. So plus e to the minus 3t, 1, 4. All right. Well, great. Now, there is a question, how do we write the answer? Because notice the way the question has been phrased to us. Find the particular solutions x1 of t and x2 of t. So it could be saying you really should write it as x1 of t equals x2 of t equals. And so we're going to do that. So remember, this right here is equal to x1, x2. So we can now just read it off. So the top is x1. So you can say x1 would be 4 e to the 4t plus e to the minus 3t. See, right? 4, there's 1. And x2 would be 2e to the 4t and plus 4e to the minus 3t. And there we have our nice answer. x1, x2. Boom. Done. Done. Eigenvalue method problems aren't so bad. It's really about, you have to say, hey, find the eigenvalues, find the eigenvectors associated. In this case, no surprises, nothing too exotic happens. Put it together, get our general solution. And if needed, find the particular solution. So, all right. No surprises? Great. Well, let's keep going. So, what's next? Probably number 3. That's usually what happens with these problems. They tend to go nice and sequential. All right. Consider the linear ODE. Remember, ODE is just shorthand for saying this is an ordinary differential equation, the kind that we would see in this class. X prime equals t to the -1, t squared, 4t to the -4, and t to the -1, x. Now, you're like, what? Look at this matrix. Wow, they're not numbers. There's functions of t. Can we have that? And the answer is, yeah, of course you can. Of course you can. In fact, that's how we introduced it. You said, you can have this general setting where our coefficients are functions of t. But then we said, we'll spend all our time focusing our energy when we have not coefficients as functions of t, but rather just have it be constants. And then we have our methods. So, okay, great. Now the problem is, eigenvalue methods don't work on this. The good news is we don't have to, because look at what it's asking us to do. Part A. verify that this t to the fifth, 4t squared, and minus 1t to the minus 3 are both solutions to this system. Okay, so just on a side note, we would be writing this as x prime equals a of t x. So normally it's just a constant. A of t just says things very perfectly allowed. So how do you verify things? Don't try to verify by saying, oh, I'll find the solutions and just check that I got the same answers. That's the worst way to verify things, because almost always that way involves pain and suffering and things that we don't know how to do. The best way is just say, well, hey, we just plug these in to both sides and we compare the answers. And if the things match, verified. And so in some sense, part A is a beautiful thing because this should be free points. It's just plug things into both sides and they match. And if they don't, okay, we made a mistake, go back and check our work until they do. So we have to do it twice for each one. So let's start with the first one. Suppose we have our t to the fifth and 4t squared. So there's our x. So we're going to look at x prime. And the way we look at x prime is we take the derivatives. So that would be 5 t to the fourth, and then downstairs, 8t squared. Okay, well that was not so bad. And now, the next part is we're going to look at the other side. Okay, so we have t to the minus 1, t squared, 4t to the minus 4, and t to the minus 1. And we're going to multiply that by t to the fifth and 4t squared. All right, so t to the minus 1, t to the fifth, that would be t to the fourth. T squared, 4t squared, 4t to the fourth. T to the fifth, 4t to the minus 4, well, that would be what? Oh, whoops. Why did I put 8t squared? Just 8t. See, I got nervous because I was like, t to the fifth times 4t to the minus fourth, that's not 8t. That's not anything t squared. That's something t. But, well, made a small error. You know, you'll see, I make small errors, but I catch them. And that's how I'm able to get my points. You got to fight for every point. 4t. t to the minus 1 times 4t squared is 4t. And put it together, you get 5t to the fourth and 8t. And now we say, hey, once I fixed my mistake, these are match. And so verified. Put a little check. All right. Well, now we just do the same thing for the other function. So no big surprises. So here we go. Hopefully, this time, less likely to make small mistakes. Well, less likely doesn't mean unlikely. But, all right, x prime. Well, derivative of a constant is 0. I know that one. Derivative of t to the minus 3. Minus 3 comes down, t and minus 4. Remember, subtract 1 from minus 3 gives minus 4. Okay, now do the multiplication. T to the minus 1, t squared, 4t to the minus 4, t to the minus 1, times minus 1, t to the minus 3. And let's see what we get. Well, we're going to get minus t to the minus 1. And then we're going to get t squared t to the minus 3 is plus t to the minus 1. Here we'll get minus 4 t to the minus 4. And then we'll have plus t to the minus 4. And upstairs they cancel. And downstairs minus 4 plus 1. Well, that makes minus 3 t to the minus 4. And we're like, aha! They match! Yes, exactly. Well, they should match. That's what verification is about, making sure things match. Since everything matches, life is good. And now we're ready to go on to the second part of this problem, part B. Find a solution to this ODE system with x of 1 equals 5, 5. So notice it's not x of 0, it's x of 1. And, well, that's actually a good thing, because if you plug 0 in here, weird things happen. because you get t to a negative power at 0. Whoops, that's not going to work out. Yeah, definitely going to get problems. But what do we have? Well, we understand the theory. The theory says if we have solutions, we can take superposition of them, which means, in other words, linear combinations, because it is a linear type ordinary differential equation. Now you might say, well, how do we know it's a linear ordinary differential equation? The secret is it tells us right here. See how it uses the word linear ordinary differential equation? That's a pretty good clue. And so that's when we can apply superposition. So we say, okay, so what we should really be looking for is we should be looking for some linear combination of these two solutions. So I have t to the fifth and 4t squared, and then b minus 1 t to the minus 3. Now, what do? Well, let me move this up. We're going to plug in time 1, and we want to get 5, 5. So x of 1 should be 5, 5. Well, that's the same as a, plug in 1, get 1, 4, plus b, plug in 1, minus 1, positive 1. It's really easy to plug in 1. All right, well, so, okay, what does that tell us? Well, it tells us that a minus b needs to equal 5, right? Just a minus b equals 5. And 4a plus b should also equal 5. And beautiful. Look at that. We can just straight up add these two together. And if we do that, hardly any work at all. 5a equals 10, which tells us that a better be 2. And once we know that a equals 2, I'll just pick whichever equation you like. You can say, okay, so let's suppose I pick the second equation. 8 plus b has to equal 5. Well, what when I add it to 8 gives 5? Oh, well, that says b has to be negative 3. All right, well, now we found a and we found b, and that means life is good because we now have our solution. We just put it all together. So we come back here, put it a equals 2, and put b equals negative 3, and we're going to get 2 t to the fifth, 4t squared, and minus 3, because that's a equals 2, b equals minus 3, and minus 1, and t to the minus 3. And there we go. There's our solution, which satisfies that when we plug in 1, we get out 5, 5. So, woohoo! Nice! Nice. Now, on a side note, I like this problem because I wrote this problem. This is my problem. I really like it just because it's something a little different. We're not used to seeing functions of t into there, even though we said, yeah, it's a possibility. But then we sort of said, we're never going to look at anything other than saying it's a possibility because it's hard to solve. It's really, really hard to solve. But doesn't mean that it can't be encountered. It doesn't mean that we can't do some very basic things. And the other thing is that we actually have a 1. I almost always say, well, at time 0, at time 0, at time 0. Yeah. But maybe time 1. And it has to be at time other than 0 here. Because at time 0, all sorts of crazy stuff happens with this differential equation. It just breaks down. Okay, so there we go. That's number 3. We're like halfway done because we're halfway done, right? So let's move on to number 4. All right. So here we go. Consider the system x prime equals 1 minus 1, 1, 3x of differential equations. And now find the fundamental matrix, phi of t, of the system. Now, it's helpful to remember what is the fundamental matrix. So the idea of the fundamental matrix is what you do is you're going to have phi of t, and we put in some, say, x1, x2, where these are linearly independent, so that's what the Li means, linearly independent solutions. And it's not unique, this phi. There's infinitely many correct answers because you can do lots of scaling and combining of things, so there's many, 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 many possible ones. Now, just because there's many does not trivialize having to find one. It's still work. And so we shouldn't take this lightly. And we won't. We won't take it lightly. We will make sure to engage and follow through. Okay, so where do we go? Well, we are going to find solutions, right? Because we need two solutions. And they have to be linearly independent. It's not enough to find one and say, aha, I'll just copy. They have, got to get all the solutions. That's really what phi of t is doing, is find a way to somehow get all the solutions packed together. All right, so, well, we're back into our nice, numbers here. And so we should start by talking eigenvalues. All right, so we're going to look at determinant of a minus lambda I. All right, so that's 1 minus lambda, minus 1, 1, 3 minus lambda. And if we take that to determinant, 1 minus lambda, 3 minus lambda, and then we're going to subtract 1 times minus 1. Well, that's lambda squared there. Then we get minus 3 lambda. Minus lambda is minus 4 lambda. And then plus 3 plus 1 plus 4, which makes us lambda minus 2 squared equals 0. Which means that we have repeated roots. Ooh. Now, the reason why we make the ooh sound is like repeated roots. It says that there's a potential that we don't have enough eigenvectors. No, not necessarily. Don't panic yet. Wait a little bit before panic sets in. But realize that there's an opportunity for us to justifiably say, uh-oh, we maybe should panic a little bit on this one. So let's see where the problem takes us. So the next thing is we know our eigenvalues. So we'll make a little list here. Are 2, 2. All right, so eigenvectors. So we're going to look at a minus 2I. Okay, so what does that look like? Well, that looks like minus 1, 1, 1 times a b. And we want that to equal 0, 0. Well, it doesn't really matter which one you look at. You either have minus a minus b equals 0 or a plus b equals 0. So that says our eigenvectors has to have that a equals negative b. So we're like, okay, so ab is going to look like minus bb, which looks like b minus 1, 1. So there's one eigenvector, which is great. So we can write that down. Eigenvector, we have minus 1, 1. And now we say, well, where's the second eigenvector? And the answer is, we don't have one. Now, that's not to say there aren't other eigenvectors. For instance, if you multiply b equals 2, minus 2, 2, or b equals negative 1, 1, negative 1. The problem is, it's the same eigenvector up to scale. It's not linearly independent. And so, we are short. Bum, bum, bum. Uh-oh. What do we do? Well, what we don't do is panic, and we don't come up with some creative thing that doesn't work. We say, okay, great, this is the case where we're short an eigenvector. So we'll call this here, we'll call this our v. So now what we need is we need to find some a minus lambda I times u equals v. So we need that. Because then when we're short eigenvectors, it's sort of our bootstrapping, it's our bumping that has to go on. So we know what a minus lambda I is. That's the same vector here. So minus 1, 1, 1 times u. Well, okay, we'll call it u1, u2 equals v, and minus 1 plus 1. And now we have two equations and two unknowns. Okay, so what does this become? Well, this becomes minus u1 minus u2 equals minus 1, and then u1 plus u2 equals plus 1. And we need to find any valid solution that works. And there's many. In fact, if you look at these two equations, you'll notice they're actually the same, up to a minus sign. So you say, look, okay, I can knock out one of the equations. So I need to find any solution that says u1 plus u2 equals 1. Anything that does that, that'll work. All right. So can you think of solutions? I can think of a lot of them. u1 equals 1, u2 equals 0. u1 equals 0, u2 equals 1. But many, many work. And you'll have infinitely many that work. You only need one. So you can say, okay, so here's one possibility. Say u1, u2, we'll say is 1, 0. All right. Now, what's the point here? Well, the point here is that we have our solutions. Now, we get one solution because we do have an eigenvalue-eigenvector pair. So we'll call that x1. And that looks like our e to the eigenvalue t times our eigenvector. And then we have a second solution, x2. And x2, well, that's going to be similar. You have e to the 2t, and then you have t times your v minus 1, 1 plus your u, 1, 0. All right, so there's our x1 and x2. These are two solutions, and they are linearly independent by construction. So, are we done? Well, not yet, because it says find a fundamental matrix, so we have to write it in this format. So, we're going to have to dip a little bit into the space for part B. Hopefully we don't need too much space. So phi of t, well, we have minus e to the 2t, e to the 2t, that's the x1. Okay, so I'm just going to make a little note here. This is our x1. And then x2, well, we have our 1 minus t, e to the 2t, see 1 minus t, and then we have our t, e to the 2t. So this is our, sorry about that, this is our x2. So there we go. There's our phi of t. And we're done with part A. All right. So this one is interesting because there's sort of two things that happen at the same time. One, we have to understand what phi is and how to make it. And two, we have to deal with the case, what if we're missing an eigenvector? And we have to make sure, like, hey, we know how to do both of those at the same time. And if we do, it's not too bad. And if we don't, because we're going to need this for part B. Because what is part B? Oh, part B, we move it up, says use phi of t. Oh, so here we good news. We found it in part A. To find e to the at. Okay, so here we go. All right, so how do we do it? Well, the answer is it turns out e to the at is a fundamental matrix. In some sense, it's the special fundamental matrix. And we have this nice basic fact that e to the at is equal to phi of t times phi 0 inverse. So if we find phi 0 inverse, and we have phi of t, then do the multiplication, we get e to the at. All right, well, let's do the work. So first off, what is phi of 0? Well, the nice thing is e to the 0 is 1. When we plug in t equals 0, you get, well, t equals 0 is 0, right? So a lot of things simplify pretty nicely. And we get this matrix minus 1, 1, 1, and 0. Okay, so that's 5, 0. Well, that's nice. That was about as good as we could hope for. Now, are we done? No. We need to find the inverse. You can find it by doing augmented matrices, or you can remember there's a formula. We'll use the formula because we need our space. So phi 0 inverse, well, take the determinant. So 0 subtract 1 would be negative 1, so 1 over negative 1. And what's the rules? The rules are you swap the diagonal entries, 0, minus 1, and then you flip the signs in the two off diagonals. So minus 1, minus 1. Well, that becomes, because you can multiply the minus through, 0, 1, 1, 1. Now, because we want to make sure we get our points, let's check that this is the inverse. And the way we do it is we quickly run the multiplication. 0 plus 1, that's 1. Minus 1 plus 1 is 0. 0 and 0 is 0. 1 and 0 is 1. It makes the identity when you multiply those two together. It means it's the right inverse. Okay, so what do we do to finish the problem? Well, we're going to take phi of t times this matrix. So we're going to get minus e to the 2t, 1 minus t, e to the 2t, e to the 2t, and t e to the 2t, times 0, 1, 1, 1. Okay, well, let's do the work. All right, so 0 plus 1 of those. So that 0 is out, plus 1 of those makes 1 minus t e to the 2t. Then we're going to get minus e to the 2t. So I'll write that down, minus e to the 2t, plus 1 minus t e to the 2t. Here we're going to get 0 plus t e to the 2t. And then lastly, we'll get e to the 2t plus t e to the 2t. And if we clean that up just a little bit, just enough. 1 minus t e to the 2t, t e to the 2t. Here, well, if you work it out, see how you have a minus e to the 2t and you have a plus e to 2t? They cancel each other. So we have minus t e to the 2t. And then here, let's just pull an e to the 2t out. 1 plus t e to the 2t. Now, one thing that's nice for people who are the graders is it turns out that phi of t is not unique. There's many, 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 many correct answers. But e to the at is always going to be the same. Now, is there anything you can check? Well, there is one quick check you can do. When you plug in t equals 0, you should get the identity. And you can see that when we plug in t equals 0, those terms go to 0. And on the diagonal terms, you go to 1. So that's a good sign. It means we probably did it right. All right, cool. Now, I want to pause and say, this problem could have been done in a different way. So let me just mention that, hey, let's talk about what could have happened. And we'll compare the answers in just a second. So we could have said, okay, we're considering the system of differential equations. Oh, all right. Well, hey, let's do that. Find our fundamental matrix. And say, all right, well, we've got to start by finding our solutions. So we better, talk about our eigenvalues. And so we do what we did before. We're going to say, all right, let's look at a minus lambda I. Take that determinant. And I'm just going to skip the intermediate steps here. And we say, aha, we get lambda minus 2 squared equals 0. And we're like, oh, all our eigenvalues are the same. And so, here we are taking our test. And we're like, And so we have our little thought bubble here. And it says, oh, all eigenvalues are the same. All right? That's our little thought bubble. And then we say, oh, now why do we have that little thought bubble? We say, hey, you know, it says find the fundamental matrix. But actually, we know that really there's many fundamental matrices. And we say, oh, we can find a nice fundamental matrix. So we're going to come down here right away and say, we're going to find e to the at, because that will work. You might say, what? How can we find e to the at faster than solving this system? Well, let's copy what we have. We have that a is equal to 1 minus 1, 1, 3, and our eigenvalues are both 2. So there's this really cool fact. And, well, there's actually two really cool facts. So let me write them both down. So one really cool fact is that e to the at, that's the identity, plus a times t, plus a squared, t squared over 2 factorial, plus dot, dot, dot. The other nice fact is it turns out that e to the lambda t times e to the a minus lambda I t is equal to e to the at. And this is true for any lambda. Now you might say, what? When did we learn that? Well, it was a problem on the practice test. It was like, hey, here's a secret. And now it's like, oh, so that's why Steve put that one on the practice test, just so he could pull this out at just the right moment and say, look at it, it could be done in a really fast way. Whoa! Did anybody do it this way? No! But, you know, I just want to show you that there are options. I'm just having fun. You know, shouldn't you have fun when you're doing math? I think the answer is yes. All right, well, what happens? So, what's a good choice for lambda? Well, the eigenvalue is a good choice for lambda. So we say, okay, great. Let's do our little note here. So we have e to the at is, according to this, e to the 2t, because I'm choosing lambda equals 2. And then we're going to have e, and now we're going to have a minus lambda I, which is a minus 2i. So that's going to become minus 1, 1, 1, t. Okay, all right. At this point, I'm like, sure, Steve, I'll give it to you. But what happens? This is e to the 2t, and now I'm going to pull out this part. It's the identity matrix, 1, 0, 0, 1. Okay, plus a times t, all right, minus 1, 1, 1, times t. And what comes next? Well, let's do a quick computation. What's a squared? Sorry, what's this matrix squared? So minus 1, 1, 1, times minus 1, 1, 1. Well, you'll get 1, minus 1, 0. 1, minus 1, 0. Minus 1 plus 1, 0. Minus 1 plus 1, 0. Which means all these other terms are gone. So when all of your eigenvalues are now 0, and that's what happens after you, see, if all your eigenvalues are the same, if you look at the matrix, where am I pointing? A minus lambda I, it says, oh, make all your eigenvalues of that matrix 0. And if all your eigenvalues are 0, what's going to happen is, after just a few steps, you get the 0 matrix, which means that you don't have infinitely many things. The dot, dot, dot means, oh, this looks hard, infinitely many things. No, no, no. Only finitely many. In our case, we stop after 2. And so we say, okay, well, what does that tell us? All right, well, that tells us we have e to the 2t times the matrix 1 minus t, t, and 1 plus t. Or if you multiply the e to the 2t through, we'll get 1 minus t, e to the 2t, minus t, e to the 2t, and t, e to the 2t, and 1 plus t, e to the 2t. And there's the answer for part B. Now let's pause, because we're not done with this problem. We haven't you have to go back to part A. But let's pause and just say, here was our answer before, here's our answer now, and what do you see? They're the same. Wow! Isn't that cool? There's more than one way to solve a differential equation problem. Woo! Life is good. Now, but you might say, well, wait, how does this help us with part A? Well, remember, part A says you just need to find one of them. This is one. So you just copy it. So 1 minus t e to the 2t minus t e to the 2t t e to the 2t and 1 plus t e to the 2t. And we'll call that 5t. Because e to the at is a fundamental matrix. So you could actually have done part B and then use the answer for part B to find part A. Now, the only reason we probably wouldn't want to do that is it can be kind of hard to find e to the at unless you know what you're doing. But that's not so bad. Just needs a little bit of thought and a little bit of practice. Okay, now, do I recommend you memorize this? No. This is more of a fun, like, hey, isn't this cute and adorable? Look how adorable it is. Like, oh, it's so cute. But just because it can be done this way doesn't mean it should be. But it's nice to see that, oh, hey, isn't this amazing? Sorry, I just love this. It's just so cool. Just so cool. All right, well, that 4 problems, that means 2 problems left. And I'll tell you that we're getting to the part of the test where I spent the most amount of time grading. So I'll probably have a lot more comments about mistakes people had for the next 2 problems. Okay, number 5. Find the inverse Laplace transform of f of s equals 2s minus 3 over s cubed plus 5s squared. Now, if you look at the denominator, well, you see there's a common factor of s squared. So you could say this is 2s minus 3 s squared times s plus 5. All right, now one mistake that I saw a little bit too often was people planning on saying like, oh, like s and s squared plus 5. No, be careful. You know, what do we have here? Now, the next thing that happened, and I'm not going to do it here, not yet, is people said, oh, hey, let's break it up upstairs. And what does that mean? Well, they said, oh, let's think of it in the following way. Here, I have another copy of the problem. So they said, you know what we really could think of this as? They said, let's say, because we have 2s minus 3 over s squared times s plus 5, why don't we think of this as 2s over s squared times s plus 5 and minus 3 over s squared times s plus 5, which of course becomes 2 over s times s plus 5 and minus 3 over s squared times s plus 5. Now, can you do that? Well, yeah, I just did. Would you want to do that? Probably not. And yet, I did it because I'll come back and say, there is a case where it makes sense. But what's going to be our next step? What's sort of the intuitive thing to be doing here? Well, the intuitive thing to be doing is partial fraction decomposition. And you might say, well, why not just do 2 partial fraction decompositions? And the answer is, it's just as easy to do this one. In fact, it's easier than to do 2 of them. There'll be just as much work to do just these 2 are going to be the same amount of work. And then you have to do more work. So it's more efficient to just put it all together before you pull it apart and in partial fractions. So if we're doing partial fractions decomposition as our approach, it makes sense to leave it together. So that's what we're going to do. Now, if we aren't doing partial fractions, there are other options. This can make sense. We'll get to that in a minute. But, okay, so what do we do? What do we do? Well, we do the following. We need to know the form. So in some sense, the hardest part about partial fractions is making sure we have the right form down. So we're going to say 2s minus 3 over s squared times s plus 5 is something over s plus something over s squared plus something over s plus 5. So in our case, the numerators are always just numbers. There's no, as plus b. And you might say, well, wait a second, there's a square there. Don't we need to have... No. Look, it's the s you're queuing off of. And so there's no irreducible quadratics in your denominators. So nothing that you need to worry about. Oh, okay, all right, okay. Well, now what? Well, now we clear our denominators. Okay, well, so multiply both sides by s squared times s plus 5. And so that's what we're going to do. Now, I will say some people, when they're like, oh, when I clear my denominators, I'm going to multiply by s and by s squared and by s plus 5. And no, don't do that. Don't do that, because that's the wrong thing. When you're clearing denominators, use this piece. This will always clear out the denominators. So we end up with 2s minus 3 is equal to a times s plus 5 plus b times s plus 5 plus c times s squared. And now we say, what do we do? Now, there's options. There's actually lots of options. And ultimately, at the end of the day, it's just like, how do you make two polynomials equal? Now, my preferred method, and the one I'm going to start with, is say, are there some good choices we can make? Good choices are things which make term 0 on this side. And I see two good choices. And they are 0 and negative 5. So let's plug those in. Well, actually, let me keep switching colors. I want to make sure I want to be known as the colorful differential equations professor, right? Because I use the most colors. Okay, so plug in s equals 0. We're going to get negative 3 on the left-hand side and 0 there, 0 at the end. And, well, that's 5b. Okay, so b should be negative 3/5. That wasn't so bad. All right, let's choose another one. Negative 5. Okay, so minus 10 minus 3. Ugh. Well, all right. It is what it is. Minus 13. All right, 0, 0. Then, well, minus 5 squared is 25. So 25c. So we see that c is equals negative 13 over 25. Now, if you're looking at this and saying, wow, these are unusually unpleasant fractions, you're right. Because what happened was initially this had been a slightly different problem. And then we said, well, let's just tweak the denominator a little bit. And we forgot, oh, we should also tweak the numerator to help make sure we get nice answers at the end. We're like, well, there's going to be answers. Well, doesn't mean they're going to be nice looking answers. So I apologize for these fractions. Okay, so in some sense, we're 2/3 the way done. Now, what comes next? Well, there's not a good choice. And given that b and c are not pleasant fractions, I don't want to throw in a number that can give us some weird things to play with. So what I'll look at now is look at coefficients. So if, for example, we look here, say, well, what about s squared? Well, there's two places s squared shows up, c and a. So a plus c. S, well, there's a 5a and a b. And somebody wrote on their test, 5 and s are not good to put together. I agree with that assessment. I am very much like, I get you. I know where you're coming from. We are simpatico in our feeling about putting 5s and s's on the same problem. So 5a plus b, and of course the constant would be 5b. And now we say, well, hey, there's no s squared over here, so that says that this part has to equal 0. So we get that a plus c equals 0, or a equals negative c, which means that a has to be 13 over 25. Because we know what c is. It's negative 13 over 25. And now we're like, wow, we've done it. We found our A, B, and C. We've got all our constants. We can write our answers. Well, an intermediate answer for our partial fraction decomposition. So we have the following. We can say that 2s minus 3 over s squared times s plus 5 is equal to, well, 13 over 25 times 1 over s, and then minus 3 over 5, 1 over s squared, and then plus 13 over 25, 1 over s plus 5. All right. And great. Now, why have we done this? Well, we've done this because by pulling it apart, we have things that fall in our table. So let's check our table. Okay, 1 over s, that's there. That'll just be 1. 1 over s plus 5, yeah, that's no problem. Where would that be? Oh, here we go. 1 over s plus 5, that's like a equals minus 5, so that would be an exponential function. And, okay, s squared downstairs. 1 over s squared, well, that's coming here. So if you look at that, s squared would be n equals 1. 1 factorial over s squared. Great. Well, that means it becomes t. So we now have taking the inverse Laplace of both sides. Well, we get 13 over 25 times 1 minus 3 over 5 times t plus 13 over 25 e to the minus 5t. And that's it. There we go. Whew. All right. Well, that was not so bad. What was the thing I was rambling about before? Well, let's go back and say, hey, here's options. And we'll compare our answers in just a few minutes. Maybe more than just a few minutes, depending upon how long it takes for us to do our options. Now, when you look at this and say, well, how could we do this problem and without doing partial fractions? Well, we're going to use a couple of basic facts. We're going to use one fact, which is on the table, and I'll just write it down here. So, namely, the inverse Laplace of 1 over s plus 5 is e to the minus 5t. Okay, so we have already used that, so that's not too surprising. Now, the other part is it's actually not on the table. And so you might say, wait a second, we can use stuff that's not on the table? And the answer is yes, yes, you can. And you might be saying, well, what's the stuff on the table that we could have used? And here it is. The Laplace of the integral 0 to t of f of tau d tau is the same as the Laplace of f of t over s. So somehow integration translates to division by s. Now, working backwards, we can say, oh, division by s becomes integration. And if you don't like the word integration, you can say it in a slightly different way. Instead of saying integration, you could say antiderivative, where the constant at, the value at time 0 is 0. Okay, so let's do it on these pieces and see what we get. Now, again, this is not the way I would recommend, but just because it's not the way I would recommend doesn't mean that it doesn't work. And so it's like, hey, we've got time, we're young, let's go for it. And let's see what happens. All right, well, let's do it. Roll up our sleeves even further because we're going to need some energy to get through this. All right, so let's start with 1 over s times s plus 5. So if I'm doing Laplace inverse of 1 over s times s plus 5. What this really says, see, because we can think of this as there's that factor of s there. So it's like, oh, it's like I did the Laplace inverse of what is 1 over s plus 5. Well, it corresponds to e to the minus 5t. And so we say, okay. So what this will be is it will be the integral from 0 up to t of e to the minus 5t dt. Okay? So again, the logic here is when you divide by s, then you say, all right, take the rest of the function, which is the 1 over s plus 5, which is what you have there, and then you integrate that function from 0 to t. Well, that's not a bad function to integrate. That would be minus 1/5. Whoops, not t's, tau's. Minus 1/5 e to the minus 5 tau, evaluate 0 to t, which would become, well, minus 1/5 e to the minus 5t, plug in 0, minus 1/5 is plus 1/5. All right, well, that's that part. Move our paper up. We also need s squared over s plus 5. Well, how do we do that? Well, 1 over s squared times s plus 5 is s times s plus 5. So it's like, oh, I can think of it as here's my divide by s piece. So I say, all right, that's the integral from 0 to t of what's the inverse Laplace of s times s plus 5? Well, it's that. So minus 1/5 e to the minus 5 tau plus 1/5 d tau. Well, that's, what will that be? 1 over 25 e to the minus 5 tau plus 1/5 tau. And we're going to evaluate that from 0 to t. When we plug in t, we get 1 over 25 e to the minus 5t plus 1/5 t. Subtract, plug in 0. You get 0 there, but we get something here. So subtract 1 over 25. And now our final answer says, okay, what haven't we accounted for? Well, we haven't accounted for these values upstairs. And don't forget, there's the minus there. So our answer will be the following. We're going to get our 2 times this, so minus 1/5 e to the minus 5t plus 1/5, subtract 3, 1 over 25 e to the minus 5t plus 1 over 5t minus 1 over 25. Now, let's do the computations here. Here we have minus 10/5, right? Minus 2/5, minus 10/25. Here we have minus 3/25, which would give us minus 13 over 25 e to the minus 5t. 2/5, which is 10 over 25, plus 3 over 25 makes 13 over 25. Minus 3 times 1/5 makes minus 3/5 t. And that should be the answer. Now, we can check, right? Because we actually have the answer. And if we move this up so we can see them both, let's compare 13 over 25 minus 3 over 5t. And whoops, what? Something went wrong here. What went wrong? Why is there a plus 13/25 here? Because, C should be negative. Oh my gosh. C is negative 13 over 25. Well, see, this just goes to show you. Check your work. So yeah, minus. All right, well, Thank goodness we did it the second way, right? Well, you shouldn't have to do it a second way to find your mistakes. But there we go, yeah. So it works. It works. All right. Wow. All right. So, well, we have options. We have options. Speaking of options, number 6. The end. The end. Solve the following ordinary differential equation, ODE, with initial values. Okay, good. Bread and butter. This, no surprises coming up here. Y double prime plus 16y prime equals 16 u of t minus pi. Y of 0 equals 0. Y prime of 0 equals 0. And here, u is a unit step function. So you even told us what u was. We already knew that. Come on, they didn't need to tell us that. We're pros at this by now. All right, well, how do we solve it? In our case, it doesn't say that we have to use Laplace transforms, but it kind of feels like we should because it's the end of the test. That means it should be the last thing we've learned. But also, the only place where we really talked about the unit step function is with Laplace transform. So that makes sense. Okay, so we're going to take the Laplace transform of both sides. So Laplace transform of y double prime plus 16 Laplace transform of y is equal to 16 Laplace transform of u. Oh, wait, it's a fancy u. So I should make sure I put my little fancy there of t minus pi. Now, the good news is y of 0 equals 0, y prime of 0 equals 0. So x double prime, well, y double prime, same thing. It would be s squared y of s, 0, 0. Okay, so those terms go away, which is great. Good for us. So those go away. You might say, okay, x prime. We don't need to worry about x prime. I saw this on several tests. This is not the y prime, it's just y. So what do we get? Well, we get the following. This is s squared y plus 16y equals 16. Oh, they didn't talk about our unit step function, but the unit step function, t minus a, e to the minus as over s. So in our case, e to the minus pi s over s. All right, great. Well, not too hard to figure out what to do. Factor out y times s squared plus 16, okay, equals 16 e to the minus pi s over s, or we get that y is equal to 16 e to the minus pi s over s times s squared plus 16. All right, and now comes the fun part. We get to figure out, what do we do? Well, hopefully nothing should surprise you. Partial fractions. Now, two main problems happen when people did partial fractions on the next step. And the first one happened right away. So let's pause for a second and remember partial fractions, because we've seen this before. You know, we've been through Calc 2 and the joy that is advanced calculus. And even before then, we've took algebra. And so the question is, when can we do partial fractions? And you might say, well, here, we can do partial fractions here, Steve. But there's an important thing to remember. Partial fractions works when you have polynomial over polynomial. You have to have that. It has to be polynomial over polynomial. Nothing else will work. And you look at this and say, oh, wait a second. That part's not a polynomial. What do we do with it? Okay, so here we go. We're going to use some advanced, sophisticated technology called put it on the side. So 16 over s times s squared plus 16 e to the minus pi s. So in other words, that part, that's where you do the partial fractions. The e to the minus pi s is not involved with partial fractions. Put it on the side. Leave it alone. And if you try to put it in there, you get a lot of weird stuff. And depending upon choices that you make, you'll get weird answers. And unless you get really lucky, you'll get wrong answers. We don't want that. We want right answers. right answers tend to get more points, and we want the points. Okay, so let's do our partial fractions. So give ourselves some space here. 16 over s times s squared plus 16. All right, well, what is that? We need the form. A over s plus bs plus c over s squared plus 16. Now, here's a case where you do need bs plus c upstairs, because s squared plus 16 is irreducible quadratic. It means you can't factor it any further. It's as factored as it's going to get. So you have to have that little piece upstairs. A few people forgot about that. That's not the mistake that's coming. The mistake that's coming is going to be like, oh, I can't believe that happened. Oh, because I'll tell you, I saw it on so many tests. I was like, oh, I can't believe you did that. But that's not happened yet. Keep going. Okay, clear your denominators. No big surprises. We're going to multiply both sides by what's in the denominator on the left-hand side. So multiplying everything by s times s squared plus 16. And when we do that, what do we get? Well, we get that 16 is equal to a times s squared plus 16 plus bs plus c times s. Now, make good choices. There's one good choice. S equals 0. You can do that. Sure, let's just do that. If we plug in s equals 0, it's kind of a redundant choice, but given that it's the only one we can make, when you plug in 0, the last term drops out. You get 16 equals a times 16, or a equals 1. So that's nice. A equals 1. Well, what else can we do? The other thing we can do is say, hey, let's just group. So what is attached to s squared? Well, you get an a and you get a b. So a plus b. What's attached to s? Well, only c. There's no s term here. There's a c times s. And then what's attached to your constant? 16a. And what do we have? Well, the constant has to match the constant on the other side. The coefficient for c, this coefficient has to match the coefficient over here. Well, there is nothing, so that has to equal 0. And a plus b, well, there's nothing s squared over there. That has to equal 0. So that says, aha, c equals 0. That's easy. Here's a equals 1. That's why I said it's kind of redundant. But we didn't know that. B equals, well, negative 1. Excuse me. All right, so great. We've got A and we've got B. So what does that say? Well, it says the following. We're going to put that back into our partial fractions decomposition. So we get the following. Okay, y is equal to, remember it's this part, which we now did decomposition, times e to the minus pi s. So we get A, which is 1 over s, plus bs plus c, minus 1 times s plus 0. So negative s over s squared plus 16. And times e to the minus pi s. All right, where was that mistake? Okay, here it was. And I couldn't believe it happened to so many people. Because they had the right form, and they got the right coefficients, and then they said, oh, b equals negative 1, and they wrote it as minus 1 over s squared plus 16. I saw that, I'm like 20, I was like, no, why are you doing this? It hurts. It hurts to see that mistake made by so many people. So make sure, after you find these numbers, they're coefficients. So make sure it's like, oh yeah, that's multiplying something upstairs. I got to put that in there because we want the points. We want all the points. Okay, so if we wanted to, we can write this as e to the minus pi s over s minus s over s squared plus 16 e to the minus pi s. Okay, and now we're ready to take the inverse Laplace transform. So we get what? Well, now normally, just s over s squared plus 16, if we look on our table, which, well, I have the table here. If we look for s over s squared plus 16, here we go. It's the cosine function. So it'd be cosine 4t. Okay, so that would be just s over s squared plus 16. So this just part by itself is cosine 4t. Now, what happens because of that e to the minus pi s? Well, in that case, we come up to here. So if you have e to the minus as times something, there's the shift and the unit step function that turns it on. So there we go. So there's going to be a shift by pi. And the other thing, of course, e to the minus as over s is the unit step function t minus a. Okay, so taking the inverse Laplace, we get that y of t is equal to, this will be the unit step function of t minus pi minus, and then we're going to have the cosine of 4t minus pi and the unit step function of t minus pi. And there is a perfectly lovely answer. That's great. It works wonderful. You can say, oh, cosine 4t minus 4 pi, the 4 pi does nothing. So you could also have done this, and you could also say, hey, these both have u of t minus pi. So you could say this is 1 minus cosine of 4t times the unit step function of t minus pi. Okay, that's another perfectly valid answer because it's equivalent. They're the same function. All right, so that's, I think, how we wanted it to happen. Could it have been done in another way? Yes, it could have been done in another way. Should we do it in another way? Why not? We've got time. All right, and if you don't want to, yeah, just skip, life is good. So let's do it another way. Now, so same problem, and I'm just going to say, let's suppose we got to our point. I'm just going to say, okay, dot, 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 and we get to y times s squared plus 16 is equal to our, 16 e to the minus pi s over s. Okay, so let's suppose we got that far. Well, what we can do is we can pull out Duhamel's principle. You're like, what? We could? Yes, we could. And some people actually did. And so let's actually see what happens. So that says that y is 1 over s squared plus 16, and then times that by 16 e to the minus pi s over s. Now here we have to pause and say, if we're going to do Duhamel's principle, we need to understand what's happening to each one of these individually. Now you might say, wait, what does Duhamel's principle involve? Well, it involves this part, convolution. So that's what we're going to be pulling out. Okay, so, but anyways, 1 over s squared plus 16 is almost sine. The problem is upstairs we should have a 4 and not a 1. So that's okay. We'll put a 4 up here. I'll do it in a slightly different color just to emphasize what happened here for those coming along later, and a 1/4 out in front. Okay, now what do we have? We have two functions. So this is 1/4 sine of 4t, and this function, well, it's the one we started with. It's 16, our u of t minus pi. And they're multiplying together. So if we have things multiplying together, it becomes convolution. So we get the following. Y of t is the convolution of these two functions. Now this is not multiplication, that's a different type of star. This is convolution. So, well, is that an answer? No, we really need to say, what is that function? So you'd have to finish it up from here. Like, all right, well, let's just do it. Yeah, exactly. Do it. You can do this. Okay. So according to convolution, this would be integral 0 to t 1/4 sine 4 tau times 16 of unit step function. And now we have to be careful here, because what would it be? It would be t minus tau, right? So wherever you, because it's f of tau, g of t minus tau, so it'd be u of t minus tau minus pi, and d tau. All right, so now we come up with a couple of interesting observations. We say, well, what is this? And it's important to understand. Well, this part is going to be 0 if we have that tau is less than or equal to, right? Because if t minus tau minus pi has to be greater than or equal to 0, that says if tau is less than or equal to t minus pi. And it's going to be 1 if tau is greater than t minus pi. So it's that on-off switch that happens at t minus pi. Okay, well, why is that important here? Well, the thing here is, when does this kick in? In other words, at what value of t do we even get anything out? Well, in order for us to get anything out at all, we have to really start having it happen to work when t has to be pi or bigger. If t is below pi, well, what happens? T minus pi is negative, and then it's always 0. So it's 0 in the whole range if t is less than pi. And so we say, okay, we get a couple of things. This is going to be 0 if we're below pi. But what happens otherwise? Well, if we're above pi, then we say, okay, this will be 1 as soon as we're at t minus pi. Well, when t minus pi is going to work. And so we can say, okay, we can trim. And in particular, we can say it's going to go from pi up to t. Because that's going to be the only places where we're going to get something that works, of 1/4 times sine of 4 tau times 16 d tau. And this is if t is above pi. Okay, so there's some subtleties here, and I'm not doing a very good job of explaining it. But the key here is if t is below pi, this part never turns on. If t is above pi, it turns on, but only can turn on from pi forward, because that's the only case when we'll have the inside be above 0. Well, okay, so we get 0 if t is less than or equal to pi, great. Which doesn't say, it says nothing turns on before pi, which should be the case, right? Think of it as a spring. This is a spring, and it's not stretched, and it's not moving. In other words, it's a spring which likes where it's at. So nothing's going to happen until something acts on it, which happens at time pi. So it should be 0 up to pi. Now, what happens with this integral? The 1/4 times 16 becomes 4. The integral sine 4 tau, well, you have to divide by 4 again. So you end up with minus cosine 4 tau. But you have to evaluate that from pi up to t. And this is if t is above pi, which makes it what? 0 if we're below pi. And now finally, minus cosine of 4t. And then cosine of 4 pi, same as cosine 0, is 1. Minus 1 makes plus 1. And that's if we're above pi. And there we go. Now, is that the same function that we just had? Yeah, it actually is. See, let's see, can we get them both on the same screen? Here we go. Because, see, it's minus cosine 4t plus 1. They're at the same function. And here it just says, oh, you turn on at pi. Okay, perfect. So it can work that way. I don't think it's the easier way, but it's a possibility. And if we're going to do that, oh, I don't have a third copy of the problem. Well, that's okay. Why don't we kind of have something really crazy, put some stuff together? Because there's something else we could have done. Okay, so let's combine our answers, and we'll have it be the hardest of both worlds, right? Isn't that a great way to do it? Okay, all right. Here we go. So we have lots of dots. So suppose we've done a lot of work, and we come up with the following. We say, okay, look, y is equal to the following. In fact, I'm just going to copy it from here. I'm going to copy this part. So 1 over s minus s over s squared plus 16 e to the minus pi s. So in other words, we did our partial fraction decompositions. But now we're going to think about this in a different way. We're going to think about it as two functions multiplying together. And this function, well, that's 1 minus cosine 4t. No big surprise. And this function, e to the minus pi s, does that show up on our list? Is that on our list? It is. It is delta. So we can think of this as delta at t minus pi. So we go and get another convolution answer. So we get that y of t is 1 minus cosine 4t convoluted with delta t minus pi, which is what? Well, that's the integral 0 up to t, 1 minus cosine 4 tau delta t minus tau minus pi d tau. And what is this? Now, the nice thing is, it's actually amazingly easy to answer the question, because the delta says, focus all of your energy on one moment. Just think of that song, just one moment in time when I have all of my energy. That song. Just that one moment in time. So, what do we care about? Well, what we care about is, when is this part equal to 0? Because if we know when that part equals 0, then we just plug it in, and then that's the answer. And the answer is, well, that happens when tau is equal to t minus pi. Right? That's it. When tau equals t minus pi, that's 0. Now, how does that help us? Well, notice we're going from 0 up to t. And so we need to make sure that t minus pi, if we're going from 0 up to t, is going to have a positive value, or at least non-negative value. So we again encounter the issue, which is will be 0 if t is below pi. And the reason we're going to be 0, so let me say this again, is the delta function never gets to, it's like bam, never gets to do its whack, because it'll never be, the inside part won't be 0 in that range. So if we're below pi, nothing happens. Now, if we are above pi, and then it says, aha, the delta function kicks in at this time. And so the integral becomes, well, plug in t minus pi. And so you get 1 minus cosine of 4t minus pi, which we've already said, lo and behold, is the same as 0 if t is below pi, and 1 minus cosine 4t, because that doesn't make any difference if we're above pi. And we're done. And it's the same answer. So yeah, we could have done convolution with the delta function, not just with the unit step function. Now, nobody did it this way, but that's probably a good thing, because that would have been a quite an interesting answer. And it takes a little bit of thought. But options. There are always options. And that was number 6. And now you're noticing that I'm not wrapping up, because there's a number 7. You're like, what? What? I already remember 6. Okay, so where is this number 7 coming from? There were actually 2 tests that happened simultaneously. One was for 267, and then there's also something called 268, which is a little bit more added on to the class. Well, not a little more added on to the class, but it's a tighter focus in the class. They had a slightly different test, and so they got 1 extra problem. And so we'll do that 1 extra problem. So it's like, wow, it's like a birthday gift, and it's not even my birthday. You guys shouldn't have. You're so good. All right, so let's just do the problem. Find the Laplace transform of the following function. So the function is t if we're between 0 and 2, and e to the t if we're above 2. Now, we could do this by doing some sort of integration by parts and doing the definition. I'm not going to do it that way. I'm going to do it probably the more intuitive way that was meant to be done, which is to say, well, how should this function be thought of? And the answer is we should think of it as this. Well, where do we start? It starts as t. So it's t. And then what happens? Well, at time 2, it switches. So if it switches, that means there's a unit step function involved. And time 2, excuse me. So that's a t minus 2. And now we're switching from t to e to the t. So how do we do that switch? Well, the answer is, well, we're going to turn on e to t, turn off t. So e to t minus t. And you can always check, is this right? You just say, well, let's look. Before 2, this part hasn't kicked in, and it's just t. After 2, we have both pieces. The t's cancel, and it's e to the t. So yeah, that's actually right. It works. Nice, nice. Okay, so now are we ready? No. What's the problem? Well, the problem is, if we have a unit step function, t minus a, we need to have it be multiplied by a function t minus a. So we need these to look like t minus 2 functions. All right, well, let's do that. So this would be t plus unit step function, t minus 2. And then it's going to be e to the t minus 2 plus 2 minus t minus 2 plus 2. So you'll notice we did the very sophisticated replace t by t minus 2 plus 2. And, well, what happens? Well, we can rewrite this as, well, here, think of it as e to the t minus 2, and then plus 2. So you can break it apart, right? So we can write this as e squared, which is a constant, e to the t minus 2. And then here, we'll have t minus 2, and then we'll have another minus 2. All right, let's distribute. So that's t plus e squared e to the t minus 2 unit step function t minus 2 minus t minus 2 unit step function of t minus 2 and minus 2 unit step function t minus 2. And now we're ready. We'll make a couple of notes here. The transformation of t is 1 over s. And here, this is transformation t minus 2, but it's been shifted. So again, we're going to have a 1 over s. Well, 1 over s squared. T doesn't go to 1 over s. Constants go to 1 over s. So think of this as a constant. So this would be a 1 over s. And e to the t, that would be going to 1 over, and let's see, what would that be? I'm looking at my table, s minus 1. So we end up with the Laplace transform of f of t is equal to 1 over s squared. Okay, that's what t maps to, plus e squared 1 over s minus 1 and e to the minus 2s. Right? Because, you know, step function t minus a becomes e to the minus as. All right, and then we have a minus 1 over s squared, e to the minus 2s, and a minus 2 over s, and e to the minus 2s. And that's it. Now, there's things you can do if you wanted to. You don't have to, but what are things we could do? Well, you could combine if you wanted to. So you could say, oh, this is e to the 2 minus 2s over s minus 1. And if we wanted to, we could do something on the other end, but I don't think it really helps. If anything, it more obfuscates. So I don't think I'll do any more combinations. And there you go. That's it. All right. Well, that was a nice little cool down. I know we took a long time going through the problems, but of course we did a couple problems multiple times and did a couple different options. So it's a doable test if you went in prepared. And I think a lot of people did well. Some people did okay, and a few people, well, there's still a final, and hopefully that'll help. And thank you for staying so long, all the way to the end, and I hope you have a great day. Bye.